absolute extrema. And let's see if this will, there we go. Okay, so we are in 14.1, absolute extrema. And we're going to use some mathy terms to describe what we're talking about. And we're going to talk about a function f. So let's say let f be a function. Defined on some interval. And we're just going to let c be a number in that interval. So we're going to let f be a function defined on some interval, and c will be a number in that interval. Okay, we're going to define the absolute maxima and minima. So we're going to say f of c, and f of c, what kind of value is that? Is that an x or a y? Okay, it's a y. Okay, so again, it's a y value. F of c, this y value, is defined as the absolute maximum. So I'll say is the absolute maximum. Let's underline that. F of c is the absolute maximum if f of x is less than f of c for every x in the interval. Okay, so at the beginning of the semester I said we will have to write down some very mathy looking terms. By the end of the semester you're going to mature into where you just read this and you can say it in non-mathy terms. So we're talking about a y value. We're going to say the y value we're talking about is considered the absolute maximum if all other y values are smaller. Right? Isn't that what this says? Okay, that should make sense, but we want to write down the math definition. So likewise, I think you guys could fill in for me if I'm going to describe what absolute minimum is. So f of c is the absolute minimum. So f of c is the absolute minimum if, and then what do we think would change here? Perfect. F of x is greater than f of c for every x in the interval. Okay, so I think graphically you'll understand this very quickly. There's just a few things that I want to show you that can occur. And so let's do a quick sketch down here. And let's plot. I said when I taught this to someone else's class, I said this kind of looks like a first grader drawing a W. So I'm going to have it look something like this. And I would like yours to look similar. It doesn't have to look exactly the same. But I want you to notice the relative mins, and I want you to have one of them to be obviously a lesser y value. Okay, it's one lower than the other. So something that looks like this on your paper. Notice that I do not have even the axis defined with what my scale is. Okay, and we've gone through, we spent a lot of the previous time discussing how we would be decreasing, then increasing, and so let's label on here. I'm hovering around this portion. Right now we call this what? From chapter 13. a relative min. Okay, so we've got that. We would also have gone on into one of the next sections and said that portion was concave up, right? So if you want to label that, you can. Okay, and then hovering here in the center, I call this a relative max. Okay, and then down here, where I'm hovering, we had called this a relative min, didn't we? Okay, but now I can describe that using this section as the absolute minimum, right? Okay. Okay, so I've got an absolute minimum, and of course this seems fairly obvious. Okay, we know what the word absolute means. But tell me, do we have an absolute maximum? So as you've mentioned, this actually goes up, right, on both endpoints, and it's going towards positive infinity. So do I have an actual maximum? No. So we can actually put a little note here that says there's no absolute maximum. So it is possible to have an absolute minimum but no absolute maximum. So I don't have to have both extreme here. I do not have to have the absolute max and the absolute min. It's possible I just have one of them. Okay. Likewise, I could draw a similar graph, or could you actually draw a graph for me that has an absolute max but no absolute min? Could you sketch that? Yeah, go on your paper and like make one up. Make something that has no absolute minimum but has an absolute max. And if I just even consider the example I have existing, what would I have to do to change that example to fit the criteria I've written here in green? Yeah, just flip it. That's right, reflect it over essentially the x-axis. Okay, so something like that, you could draw whatever you want, as long as we have that same understanding that this can occur that I have one but not the other, right? Is that clear? Okay. So you could be asked, please provide an example, draw it, or I would just give you a graph and you would describe these types of things. Either way, I would expect you to be able to do that. Okay, we're now going to introduce a theorem. And I'm trying to think if you took like MATH1325 before this one. You didn't talk a whole lot about theorems, did you? You talked about corner point theorem. Does that sound familiar? It should. Okay, so you've had probably some applications of theorems. We're going to talk about the extreme value theorem, and these theorems are things that mathematicians have proven and said, hey, you can use it, and we should be actually very grateful for them. I want you to know what this is and what it means. Okay, so extreme value theorem. I don't know why I have an S on this. It should just be extreme value theorem. So erase that. You can abbreviate that as EVT. Okay, extreme value theorem. Of course, you want to define it before you have that abbreviation. Okay, this is going to give us a way that we are guaranteed to have both an absolute max and an absolute min. Okay, but a mathematician said there's only certain conditions that will occur where you are guaranteed to have an absolute or max and absolute min. So let's look at those. Okay, what it says is that a function f that is continuous on a closed interval it says a function f that is continuous on a closed interval, and let's say it's from a to b. So closed interval, I'm going to have this bracket from a to b. Function f that is continuous on a closed interval from a to b will have both an absolute max and absolute min on the interval. Okay, and we're talking about an interval of the domain. Okay, so we're taking like a snapshot of a function, but notice it says that it's a closed interval, and what does f have to be in? It's a word that we used in the very beginning of the semester. Continuous, right? Do you remember what that means? I think 11.3 is where we did continuity, and we said there were like 3 conditions for continuity. That's going to come back to haunt you later in the semester. You're going to have a final, right? We're not actually talking about proving if something's continuous, but you need to be able to look at a graph and determine if it's continuous. What was our kind of basic informal definition of continuity? If you had to do what with your pencil? Pick up your pencil. If you had to pick up your pencil when you're graphing it, there's a discontinuity. Okay, so we can apply this theorem and say we are guaranteed an absolute max and min if we have a continuous function over this closed interval. So I'm going to give us a graph of something, and it's only a snapshot, and so perhaps I say we're looking at the interval from -3 to +1. And quite honestly, yours does not have to exactly match mine, but you need to be able to show that you're discussing just from -3, x equals -3. So you're only going to show the portion of the graph from x equals -3 to +1. And so I'm looking at that closed interval. Could you identify the absolute max? Is there one? Yes, extreme value theorem says I'm on a closed interval. It's continuous, right? I didn't have to pick up my pencil. So do I have an absolute max? Yes, I'll have an absolute min. That's what the extreme value theorem says. Do I know what that actual value is? No, because I didn't even write it on my graph, but I can at least label I have an absolute max. Could you tell me what the absolute min is?
Yes.
You can, right? What is it? Okay, be careful. How do I write that? I'd write it as f of -3. Yeah, or I could give the ordered pair. So the minimum value itself is going to be f of -3, and I could describe it by -3 comma f of -3. Okay, so just showing you, here's a snapshot of it. It's continuous on this closed interval. Okay, so we have this idea. We have no extreme value theorem. That's going to guarantee us that we have an absolute max and absolute min. I've given you one of those examples. Let's talk about overall finding absolute extrema. And this is where everything we've talked about in the previous chapters should kind of come together. I am just looking simply to see if I have the largest y value or if I have the smallest y value, and then I'm going to classify that as being the absolute max or absolute min. So you guys actually already know how to do this. This is actually a really great point for us to review and get ready for the exam. Let me scroll down since that jumped. Any questions so far? Okay. Finding absolute extrema. Okay, so the absolute extrema, if I even just use that last example, so I did scroll down a little bit so you could see this. My absolute max is occurring where before we talked about it being a relative max, didn't we? And how did you find your relative maxes and relative mins, or your relative extrema? What test was that? So relative extrema was by which derivative? The first. And you were finding certain numbers. Critical numbers, right? Your relative extrema occurred at critical numbers. Is that correct? And how did you find those critical numbers? Set something equal to 0. The first derivative equal to 0, or also seeing Where it did not exist. Okay, so actually you should have in mind here that my absolute extrema will occur at these critical numbers, right? Okay, so I'm doing those same steps. Or just even looking at this closed interval, I found an absolute min that occurred at an endpoint, didn't it? Okay, so I'm just going to put a little note here. So when I'm finding absolute extrema, the stuff that we just talked about that I should have in my head, it should make sense, that these will, if they exist rather, I'll say if they exist, I'm talking about extrema, if they exist, they occur at critical values or critical numbers. I'm going to put values since I was talking about the y really. So they occur at critical values or at endpoints. And of course, if I'm talking about endpoints, that's going to be what we're talking about, a closed interval. So I'm going to put in parentheses, that part is for a closed interval. Okay, so all the stuff that we just said, we're just making a quick note about that. And then going further with what we discussed, what am I going to do to actually find them? Well, if I'm a step person and I like to have a spot to go back and review, the first thing I'm going to do is find all of the critical numbers, right? Because we're saying the absolute extremas are going to occur at where we had previously called them a relative max or min, but now we're going to check. So I'm going to find all critical numbers. Okay. Then I'm going to evaluate the function. So I'll evaluate f, and there it goes jumping. So let me scroll down. Okay, I'm going to evaluate f for all critical numbers. And then I'm going to put a set of parentheses and say, and at the endpoints for a closed interval, right? So if we're talking about a closed interval, I'm going to also evaluate the endpoints. So maybe it'd be better to say, and evaluate f at the endpoints for a closed interval. Okay, so I'm finding the critical numbers. I'm then going to look at the function values of these critical numbers, or if I'm talking about a closed interval, I'm going to evaluate at those endpoints. And then what am I searching for to find the absolute max? The highest one, the highest value. So I'm going to identify the highest y value and smallest, I guess I could say largest and smallest, but identify the highest y value and smallest y value. And by that, you're going to be able to determine which one's the absolute max or absolute min. So really, we're doing the same things that we did before. We're adding in something about the extreme value theorem, but this is just using the first derivative, finding critical numbers. Any questions? Okay, let's do it then. Let's do a couple of examples. I'm going to give you one to try on your own. We're going to find the absolute max and absolute min. So I'll put down find the absolute extrema for, and then let's say example A, it's going to be the function f of x equals x cubed minus 12x. And let's do it over the interval from -5 to 5. Okay, when I see a math problem, I start going through what should I be recognizing. If I see absolute extreme or anything about extrema, I'm thinking first derivative test, right? The fact that it says absolute extrema means I'm going to have to do some comparisons. And I'm also noting this has a closed interval. And I'm saying, is there a theorem that goes along with it? We just learned it, so it's easy right now. If it gets to a test, you're going to have to make sure you can recall it. That's called the what theorem? Extreme value theorem. Can I actually apply it? So you go through the conditions, and extreme value theorem says that the function has to be continuous over that interval. Well, what kind of function is this? It's a polynomial. Polynomials are continuous, aren't they? Okay, so it's going to be continuous over this interval, which tells me that I am guaranteed to have an absolute max and an absolute min. And I know that the absolute max and min are going to occur either at the critical values or at the endpoints. So that's all I have to test. Okay, so the first thing we're going to do is we're going to take the derivative, and we're going to find the critical numbers. So we are very good at taking the derivative of polynomial functions. So you guys just kind of tell me, what is it? Yeah, 3x squared minus 12. You're like, man, I feel like I've been doing that forever. Okay, the next thing you're going to do is set it equal to 0. Okay, describe what we do next. There's a couple ways it can go from here. So factoring is pretty good. Factor out the GCF, which is 3. So I'm going to have x squared minus 4. And then I can actually factor the x squared minus 4, right? Difference of squares, x plus 2 times x minus 2. Okay, how many solutions do I get? 2, right? The only way this is going to multiply to give me 0 like it says is if x plus 2 is equal to 0 or x minus 2 is equal to 0. Did I do anything with that 3? No. 3 doesn't contribute to the solutions here. So I have that x is negative 2 or x is 2. And what are those called again? Okay, these are my critical numbers. Okay. So I'm going to find the critical numbers, and I'm going to compare the y values. And I also have to check, since we're talking about a closed interval, I'm going to look at the y values for those endpoints, right? Okay, so really, let's now find f of negative 2. We're going to find f of 2. And we're also going to find, if I'm checking the endpoints, what is it? F of negative 5 and f of 5. So I know that this thing absolutely has an absolute max and min. Extreme value theorem tells me that. And all I'm doing is checking the y values to see what's the smallest and the largest. So what I maybe recommend doing, just so you can have a nice little table here, is to have a t-chart where you have x and then f of x. And so if I plug in negative 2 and 2 and negative 5 and 5, or if you want to order that from smallest to largest, however you would want to do it with your x, it doesn't matter. I just need to be able to look at this quickly. I can use my calculator if I want. I remember that I'm talking about the original function, and that original function is x cubed minus 12x. So when I'm finding f of negative 2 would be negative 2 cubed, which is negative 8, minus 12 times negative 2. 12 times negative 2 is a negative 24. So I have negative 8 plus 24. Is that right? Okay, so what do I get? 16? You guys agree? Okay, so if I find f of negative 2, it's a positive 16. What about f of 2? So I go 2 cubed minus 24. Yeah, I can get out my calculator. It is negative 16. Excuse me. Okay, now I'm doing f of negative 5. So negative 5 cubed is negative 125. Okay, plus 60. So negative 125 plus 60. Negative 65. Okay, then I do f of 5, that's 125 minus 60, so it's a positive 65. That sounds right. Everyone agree with those? Okay, Do I just leave it like this? No. I'm going to look at it, right? I'm going to evaluate. I'm going to determine what's the absolute max and absolute min. So can you help me make a determination? What's the absolute minimum? So be careful on how you respond to that. What is the absolute minimum? It's negative 65. So it really is a big deal to know the difference between the negative 5 and the negative 65. Think about if your boss is like, could you tell me where we lost the most money or where we had the maximum profit? Well, if you think about what that would look like on a graph, you're looking at time versus dollars, right? Well, you've got this ordered pair, time, comma, money. You want to give him the dollar answer, the Y value, right? Not the year it occurred. He may ask you what year did that occur, but you need to give the appropriate answer. So negative 65 is the absolute minimum. And it jumped off my screen. And I could put when x is equal to 5 or something that shows I know the difference. It's negative 5, wasn't it? When x equals negative 5. And then I'll say 65 is the absolute maximum when x is equal to 5. You guys agree? Okay. Considering all that we did in the last several sections, this should be fairly easy, which is why I'm going to say for part B, let's actually look at that same function. So I'm going to rewrite it just for the sake of my notes. I want us to do the same thing. However, I want to look on the interval from negative 3 to 1. So do the same thing, right? The instructions said find the absolute extrema for this same function. So I've done a lot of the work. But now I'm looking at the snapshot from negative 3 to positive 1. Okay, so you already have the critical numbers. We did that for part A, and the respective function values, which is what you're actually comparing. So the only thing that you really had to do was to check the endpoints. Is that correct? You had to check negative 3, and you had to check when x was 1. So could you tell me about the y value, or could you tell me rather what f of negative 3 turned out to be? What is it, 9?
Yeah.
Is that right? Okay, and what about for negative, or excuse me, it was positive 1. I don't know why I have a negative here. Yeah, the interval was from negative 3 to positive 1. Oh, that's probably why I wrote down. Is it negative 1? Oh, negative 11. I don't know why I wrote down that. Okay, so you have that. And then you had some information from before, right? What were your critical numbers? 2 and negative 2. Okay, so f of 2 we had above, but y'all could tell me. Negative 16, and f of negative 2 was 16. Okay. What was your conclusion then?
Negative 16 is absolute minimum. X equals 2.
So negative 16.
Absolute minimum. 2 is in the interval. Yeah.
Oh, really?
Yeah.
Okay, good. All right, so I knew that there were going to be some people that would look back at this and just make conclusions by adding some extra parts. And in fact, you need to take a peek at what is this snapshot actually going to. So if I look back here at even considering, because some of you may have actually looked at this negative 5, right? So negative 5 is not even in this next interval, so don't put it all in one table because now the endpoints are different. We're looking at a different snapshot of this. But look from negative 3 to 1. So what can I cross out rather?
2.
The 2, right? Okay, so then I would have absolutely gotten that wrong. So a couple things that always happen when I give this problem is people will confuse it with what we just did before. We've got things outside of it. And then also look at my critical number down here. That 2 is not within this interval. So now, in case I miss that, I'm going to erase what I had. I'm going to make sure I understand I'm only looking within this interval. And so what's my conclusion now? Negative 11 is the absolute minimum Good. When x is equal to 1. And then 16 is the absolute maximum. And you wrote when x is -2. You guys can see it keeps erasing my equal signs and my negatives. So I don't know what that's doing. You see that? Ah! Okay. Nope. It wants to leave. All right. So I throw this example in there. Just be careful, right? It seemed like it was a whole lot easier than it was. It really is easy. You just have to kind of watch your interval. So good. We've done a polynomial. The only other thing out of this particular section is we're going to do a rational function, and then we're going to do an application from 14.2. So you know where I'm going with finding absolute extrema. We're looking for critical numbers. So I'm going to give you a little bit of time for you to start looking at the critical numbers for our rational function. So I'm going to call this part C, because we're still finding the extrema. However, this is going to be f of x is equal to x plus 3 all over x plus 5. And I am going to give you an interval from -3 to 1. And so things you're thinking about right away are using the first derivative, finding those critical numbers, testing the endpoints. But am I guaranteed actually a max and a min, an absolute max and absolute min? How do you determine if you're guaranteed it? So by the extreme value theorem, which says it has to be continuous on a closed interval. So I know I have a closed interval. Is this rational function continuous?
No.
No, it has a discontinuity where? When x is equal to -5. Okay. Is -5 within this interval? No. So I am going to be continuous within that interval, so I should be able to find an absolute maximum. But that's how you need to be thinking. You need to determine if we're continuous within the given interval. So we know the function by itself has discontinuity, but we're only looking at a snapshot, aren't we? And we are continuous there. Okay, so I'm going to give you a minute to go ahead and take the first derivative, and I want you to find those critical numbers. Okay, so using the quotient rule, did we all get that f prime of x was 2 over the original denominator squared, x plus 5 all squared? Yes? Okay, I hope everyone's there. Finding the critical numbers, we've already discussed multiple times, and we'll keep reviewing it because that's the best way to recall your information on your exam. Let's review it. We're going to take the first derivative set equal to 0 or find out where that first derivative doesn't exist. Okay, we've been discussing problems like this one, these rational functions that have a constant in the numerator. Is that f prime ever going to equal 0? And I want everyone to confidently tell me that f prime of x will never equal 0. Do you remember that? Okay, so I can look at this and I can say f prime of x will never equal 0. Why was that, or how could I look at this and tell? The constant in the numerator, right? This is just going to have x values thrown in the denominator, and I'm going to say 2 divided by some number, 2 divided by another number, 2 divided by a really big number, 2 divided by a really negative number. Whatever it is, I'm still going to have 2 divided by something, and this will never evaluate to 0, right? If I have a constant there, it's never going to evaluate to 0. Okay, so I've gotten that under control. So I'm not going to have a critical number from that aspect. So now I look to see where f prime doesn't exist. And you guys are pretty good about answering that. Where does f prime not exist? So f prime of x does not exist when x equals -5, right? That's what y'all said. Okay. But then I always have to take note of this, even when I was doing the previous chapter material. I also have to determine, was this in the original domain? No, right? So, but x is not in the domain of f. Okay. There's something there instead, and we graphed this last time. What does that give me? X equals -5. What does that mean to me when I'm doing the curve sketching? There's a vertical asymptote. So when we do those intervals and we're checking what's happening on both sides of the asymptote. Well, for our case right now, we're not doing the curve sketching or anything, but do I get a critical number? That's what we're doing. No, I don't. This is an asymptote. It's not, this x equals -5 is not in the domain of f. Okay, so I don't have any critical numbers, right? So if I'm going to check for absolute extrema, extreme value theorem, I'm using it, all I have to check is actually what? The endpoints, yeah. If I don't have critical numbers, the only place where I'm going to have extrema would be at the endpoints, and I'm guaranteed I'm going to have those. So now it's just determining which is the absolute max and which is the absolute min. So I'm now going to check the endpoints. Okay, our interval was from -3 to 1. Is that correct? Yep. Okay, so I've got to determine what f of -3 looks like and f of 1. Remember, this is talking about f, the original function. F of -3 would be what? It's going to be 0, isn't it? Okay, and f of 1? You said it was 2/3? That's correct. Okay. Do I leave it like that? No, I've got to have some sort of interpretation. So what am I going to conclude? Zero is the absolute minimum. And that's when x is -3. And 2/3 is the absolute maximum. When x is 1. Do you guys have any questions over that one? Okay, so those are actually the only examples I have for the absolute max and absolute min. You did one with a polynomial that was continuous, and then the trickier ones are those rational functions. So we did one of those, and I hope we have a good idea to make sure that we can use the extreme value theorem only when we have a function that's continuous over that interval. Okay, so good. All right, let's go into the next section where we're talking about applications of extrema. The homework that you're going to see from these sections, it's mostly out of 14.1, and we're talking about profit maximization in our applications in 14.2. And so we're really just applying what we've learned in the last section. And so you will see a lot of profit functions given, and we define those or denote those as p of x. And so let's look at p of x equal to -x cubed plus 12x squared minus 36x plus 400. And it says that this function is going to be defined for x greater than or equal to 3. So it'd be written like this, and it would say, this approximates the total profit in thousands of dollars from the sale of X 100,000 tires. So if you go look at your profit function, you're saying I'm only going to look at selling greater than or equal to 300,000 tires, right? Okay. So someone describe this for us. I mean, people will actually come up with these profit functions. You have the math skills to do that, but someone handed this to us, and they are asking us to use it to find the number of 100,000 tires that must be sold to maximize profit. So I'm given a function. I've got some units. It's asking me the number of 100,000 tires that must be sold to maximize profit. And so I will actually be responding with an X or Y value. X, because it says to find out about the tires. So I'm looking to see where the max profit is. I want to know the number of tires. Okay, so I'm actually going to give you a few minutes to start working on this. Please tell me, what are your thoughts to do first? You're going to take the derivative, right? And you're going to look for the absolute max by the steps that we just did. Before you get going on this, you can tell that this is a continuous function, right? And do you have a general idea of what cubics look like? Do you know about like the ends? So if you didn't take like a college algebra course, do you know that the ends are different? Like one end has to be up and then one down. And do you know based on the negative which way it goes? If you know all that kind of stuff, you can use it or look at your calculator and verify this. Remember, we're only looking at this part where we are 300,000 and beyond, or we're going to use x greater than or equal to 3. So I'm going to turn this over to you. Okay, so you know that if we're trying to maximize our profit and we want to know the number of tires that we're going to have to sell, you're first going to take the derivative, and then you're going to test those critical values. Okay, this is a polynomial. I know that you know how to take the derivative. So this is what you had, correct? Negative 3x squared plus 24x minus 36. So some of those things that seem real easy when you take the exam, make sure you go back and just double check that your signs are right, because that could be detrimental to the rest of it. So I don't think I made any errors. All right, if you're finding critical values, you're gonna find your critical numbers by setting this equal to 0. And then what did you do next? Factored it to solve it. Okay, did you factor out a GCF? So I factored out negative 3, and if I factored out negative 3, I got to go back through because I did this real quick and start walking around. Did I do this correctly? I think so. I'm checking my signs here. Okay, so I come down and I get, do y'all have the same thing? X would be 6 or X would be 2. But I actually haven't answered what this is asking me to do, right? There's still more to this. So I'm trying to maximize my profit. Could you tell me a little bit about what I have so far? Am I going to test both of these? Why not? Yeah, it said that we're looking for 300,000 tires or more. Okay, this is 200,000 tires. So really, I think it seems like we can conclude this, but there is an endpoint, and I think we need to probably check that. And so I'm going to put x here, and then I'm going to put p of x, which is our profit. And again, like you guys said, I don't actually have to look at 2. 2 is not within that snapshot we're looking at. However, I do have an endpoint, so I think it'd be good just to have that 3 in here, right? That's our endpoint from 300,000, and then 6. And so if you plug into your calculator, you do some mental math, whatever it is, what did you get for P of 3? Okay, 373. Okay, so in terms of what this actually means, I've sold 300,000 tires, and that gives me a profit of 373,000, I think, right? Was what? Okay. And so for if selling 600,000 tires, what's the profit? 400,000. Okay. So then how did you write this as my conclusion? Yep. We must sell, or they must sell, 600,000, however you want to write that out. I'll use the word. I'm going to say we must sell 600,000 tires to maximize profit. And if I want to add, what's that max profit? It's 400,000. Okay. All right, so you guys see how this is going to work? Okay, do we have any questions over that one?